Hey, hello, welcome to another answer video. My name is Dudo and I will walk you through the question of iodine transport in water and toluene. As you might have already seen, I have been keen to sketch the situation at T is 0 3 times. You can see the layers of water and toluene which are brought into contact at time T is 0. Both layers contain 10 kilograms per cubic meter of an iodine compound. Given are two ratios, the ratio of the equilibrium conditions and the ratio of the diffusion coefficients of the iodine compound in water and toluene. The first graph I will leave and the bottom two I will use later on. Question 4.3.9. In which direction does transport of the iodine compound take place? Note that Ct over Cw in equilibrium is 10, and that at T is 0, this ratio is equal to 1. To increase Ct over Cw, we must increase Ct or lower Cw, or both. Therefore, the mass transfer is in the direction of the toluene. Question 4.3.10. For relatively short times, calculate the concentration at the boundary layer for both phases, assuming that transport only occurs by diffusion. First, realize that relative short times means that the mass has not penetrated deeply enough to affect bulk concentrations CTB and CWB, which means that they are still at Cb is 10 kilograms per cubic meter. Second, that the transport within the water equals the transport within the toluene. Otherwise, it would accumulate at the interface, leading to infinite concentrations, and hence the transport within the water is equal to the transport within the toluene. Third, you should know that at the interface the equilibrium condition is effective immediately. Therefore, at the interface, 10 times Cwi is Cti. Fourth, according to penetration theory, the mass flux is equal to the diffusion coefficient divided by delta times delta C, with delta, the penetration depth, is the square root of pi dt. Combining this gives the mass flux is equal to square root of d over pi times t times delta C. Then, if we start by combining 2 and 4, we get the following. Then multiply by the square root of pi times t and take the diffusion coefficient of water is 4 times the diffusion coefficient of toluene. Divide by the square root of dt, and now apply 3. Rearrange, and then we end at Cwi. The concentration in water at the interface is 2.5 kilograms per cubic meter. And if we apply 3 once more, then we get that Cti, the concentration in toluene at the interface, is 25 kilograms per cubic meter. So that's 10 times the concentration at the interface in water. Question 4.3.11. Which of the following figures depicts the concentration profile best? And here we have to consider concentrations for relatively short times again. Well, repeating part of the previous question or previous answer, 1. Bulk concentrations far from the interface, they will still be at CB is 10 kilograms per cubic meter. And 3. At the interface, the equilibrium condition is effective immediately. So here we have 10 times CWI is CTI. And this leaves just 2 graphs. The second one in the row above and the last one from the bottom row. I will draw them both. The second one in the row above is not possible since, for instance, in the toluene part, the slope is decreasing, which means that further from the interface, the mass flux would be higher. Even if the concentration profile is forced in some way to be like the second one in the row above, having a mass flux which is higher the further you are from the interface will result in a shape that resembles the last graph of the bottom row. I will illustrate this. Note also that the solutions for water and toluene are in the form of error functions. So the last one from the bottom row is the right profile. Question 4.3.12. In which phase is the largest mass transfer resistance situated? As you might know, the sum of partial resistances is 1 over kT is equal to m over kW plus 1 over kT. And note that the last kT is a small kt, while the first one is a capital K. To see how you can get at this expression, please look at the answer given directly after the question. M over kW is equal to m times delta W divided by dW, and this is equal to 2m delta T divided by 4 dt, where we have used the relations between dW and dt, and then this is equal to delta T divided by dt times 5. 1 over kT is equal to delta T over dt. So this is 1 times delta T divided by dt. So the largest mass transfer resistance is situated in the water phase. That was all for this answer video. I hope the next time you repair your bike with a Simpson repair kit, you will think back and remember how nice it was to learn about mass transfer with this exercise about iodine in toluene. I also hope this video has helped you and that you are ready for a test. For questions, you can always go to the forum. Good luck with the graded questions.